in this example, we think to ourselves, what can we do first? If we have this, if we know the properties, what can we do first? So let's look at 6 plus 3 times 9. Well, when I look at this, this is 3 added 9 times. So I could actually change this completely into addition, looking like 6 plus 3 added 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Well, 3 added 9 times, 3, 6, 9, 12, 15, 18, 21, 24, 27. So this is really 6 plus 27. And now I notice that this, because this is repeated addition, this multiplication, it looks like that could happen and then add 6. So, which by the way is 33. So when I look at this one, 6 plus 27, which equals 33. Okay, so we see in this problem, as opposed to doing 6 plus 3, which would be 9, 9 times 9 would be 81. Yeah, but really, because multiplication is repeated addition, we want to do 3 by 9 first, then add the 6. Okay, let's do it again. Oh, I see. Look at this. I would take a moment to try this problem before I write it. But here I go. We said that division can be rewritten as multiplication by the reciprocal, because taking 6 and splitting it into 2 groups is like taking 6 and taking half or making it into 2 portions. So I'm really thinking of this problem like that, as this division by 2 splits it into 2 equal portions. Now it's written all as multiplication, and we don't even have to ask what comes first. Not really, because if we do this first, we have, okay, half of 6 is 3. 3 times 3 would make 9. So if we do half of 6, we have 3, and 3 times 3 makes 9. But also, since it's all multiplication, I'm thinking to myself, well, if I had done this first, half of 3 is 1.5. I'm thinking dollars. Half of $3 is 1.5. 6 groups of 1.5. That's a little bit harder for my mind to wrap around, but I know that 2 groups of 1.5 is 3. So 6 groups of 1.5 is 9. Indeed, 3, 6, 9. So rewriting it as multiplication allows us to kind of work it however we want, and we end up with 9. So I do want to write that this truly is 9. Now, beware that if you, so that's really what we would do first. Even though there's division, then multiplication, we would actually do the division first. 6 divided by 2 makes 3, and then 3 times 3 makes 9. What I see a lot of people making the mistake of doing is accidentally thinking multiplication comes before division, but they're actually equal footing because of this reciprocal property. So if you accidentally do 2 times 3 first, you would have 6 divided by 6. Well, there's just 1. That equals 1 because there's 1 perfect group of 6 and 6. So beware that if you see division and multiplication, they're on equal footing. You could rewrite it as all multiplication, and then there's no question about what operation. Do we do division first or do we do multiplication first? We go from left to right. Compute 6 minus 2 plus 3. Here's another situation where we might ask ourselves, well, do I do the addition first and treat that like 5 and then do 6 minus 5? It's my wake up alarm. Or do we do 6 minus 2 first, which is 4, and then do 4 plus 3? So there's two different ways, but remember that subtraction can be rewritten as adding the opposite. So we can make this all addition by saying 6 plus a negative 2 plus 3. So now it's all addition, but it is, okay, we have a positive 6, like thinking like we have $6 in our bank account. We had a debt of 2, and then we had another addition of 3 more. So 6, a debt of 2 would be 4, and then an addition of 3 would make 7. And notice we could actually do this in any order. For instance, 6 plus 3 would give 9, and then with a debt of 2 also gets us 7. So, or if we did a debt of 2 plus 3 would give us up a positive 1 in our balance. A positive 1 plus another positive 6 makes $7 balance. So this one, so even though we see subtraction and addition, try not to do this addition before the subtraction. This is another scenario where addition and subtraction have equal footing. Okay, so this is actually equal to 7, where we read it from left to right. 6 minus 2 makes 4, and then add the 3 to get 7. Okay, now the next example says to compute 2 times 3 squared. And there's an additional one here that looks a little bit different. But I want to use our thoughts on exponents. We said exponents are used to represent repeated multiplication. So let's see, this would be rewritten 2 times, okay, this 3 squared is repeated multiplication by 3. So 2 times 3 times 3. And now they're all multiplication, so we do in any order. 2 times 3 would be 6. 6 times 3 would be 18. Or we could have done 3 times 3, which is 9, and then done 2 times 9, which is also 18. Okay. Now, this other one right here is a different way to rewrite the same problem. This is saying that 3 is being squared and 2 is being multiplied by 3 squared. Okay, so this is actually equal to 18. And what I want you to be careful about here is not to do the multiplication before the exponents. Actually, 2 things I want you to be careful of. So in my mind, right? So in my careful brain, I'm thinking, okay, make sure that I accidentally don't do 2 times 3, which is 6, and then square. So 2 times 3 squared does not equal 6 squared, which is 36. We know that it's really 18 by writing it out. So make sure you do exponents before the multiplication. Same here, exponent, the 3 is what is being squared, and then the multiplication. All right. Yay. Okay, right? So when in doubt, maybe write it out. So exponents before multiplication, because exponents are repeated multiplication. Okay, let's look at computing 4 parentheses 10 plus 3. Well, we mentioned that this is a way to write multiplication. So let me go back to the previous page where we said, okay, here it is, right? This means 3 times 5. So this is really 4 times 10 plus 3, or 4 groups of 10 plus 3. So there's 2 ways I can actually think about this. I can think about this as, so if I'm being literal with my multiplication, 10 plus 3 is added 4 times. 1, 2, 3, 4. Yeah. So, okay, I see 13 plus 13 plus 13 plus 13. Or if you want to write it like this, 4 times 13. Okay. But that also tells us, which by the way is 52. If you add all of these up, 10, 20, 30, 40, 43, 46, 49, 52. But I also noticed that, so that would say do the parentheses first. So the order of operations here would be do what's inside the parentheses, then multiply. I also see that there are 10 fours. So 10 is added 4 times, in addition to 3 being added 4 times. So, and this is where we see the distributive property coming out, where if I did 4 times 10 plus 4 times 3, I would also get 40 plus 12. So doing multiplication before the addition, like in number 1, this example number 1, and that would also be 52. So just to show even how that distribution property helps us along here. So there's actually 2 ways to do this, 3 apparently. Way number 1, write out all of the things that are inside or that are being repeatedly added. Or just do the 10 plus 3 first to get 13, then multiply by 4 to get 52. Or use the distributive property where we do 4 times 10 to get 40, plus 4 times 3 to get 12, and then add. Ah, look at this. So this scenario is one of those where there are parentheses involved that are implicit or implied, but not explicitly written down. So there are parentheses happening around the numerator and denominator here. I'm going to just put them in for my brain's sake. Okay. So what we want to be careful to do here is to actually do, let's go ahead and compute this entire numerator. If you add up all of those numbers, okay, let's see. Is there an easy way to add up these numbers? Yeah, I see. You know what? I'm going to use different colors to keep track in my mind. 16 plus 14 makes 10, 20, 30. Okay. And then if you want to use the calculator, that's fine. Let's see. Do I have any other easies? Like 17 and 13. Those combine to make nice groups of 10 as well. So 10, 20, 30. Do I have any more of those that are super? Yeah, I have an 11 and a 9. That's a nice one. 11 plus 9 is 20. The rest are like so-sos. So let's see. Why not? How about let me do, how about this 17 and this 12? That's 29. And okay. I see. So 15 plus 16, actually that's 31, right? Because 15 plus 15 plus 1 is 30 plus 1. Oh, look at that. That ended up being super nice because 29 and 31, right? We can add 1 from over here to get 30 plus 30. Huh. Okay, so here's what I see. I see 30 plus 30 makes 60, plus 30 plus 30 makes 6. So 60 plus 60 is 120, plus 20 makes 140. Okay, so I actually see that entire numerator is 140. This denominator is 10. And so that makes 14. Okay, so on this one, we just really need to be careful that there are these implied parentheses. And honestly, if you took this and divided every number by 10 and added up, you would also get 14. I wonder if I could show that on my old trusty calculator. Okay, so okay, let me clear out what is in there. And let's see. So divide each one of these and it will move the decimal place. So for instance, 16, right? How many tens are in 16? Well, there's one complete group and then 6 tenths left over. So 1.6. So if I divided each one, so 1.6 plus 1.2 plus 1.1 plus, okay, divide by 10 plus 1.7 plus 1.4 plus 1.3 plus 0.9 plus 1.5 plus that got divided by 10. So that's 1.6. And 17 got divided by 10, 1.7. And notice that also added up to 14. So either you can divide every single thing in that numerator by 10 and then add, or what's usually easier for my brain is simply to make sure that I remember that a fraction treats it like implied parentheses around the entire numerator and around the entire denominator, and then divide. So add up the numerator, and then this denominator was kind, and go ahead and divide after that. Oh, but look at all of these parentheses. So who comes first? What do we have here? Here we go. I'm going to put this step by step. I see a couple of sets of parentheses. So I'm going to do a couple of things here. Let's see. I'll go purple style. In the numerator, I see this set of parentheses. Okay, so that's a thing in its own right. But even inside of that, I see this set of parentheses. So that's something to do first as well. And remember, we just talked about how in a fraction, there's implied parentheses around all of the numerator and all of the denominator. And then I see one more set of parentheses that is happening in this denominator right there. Okay, so let's work. If I just look at the numerator, because there's a lot happening there. So you know what I'm going to do? I'm going to take my piece of paper and I am going to cover up this denominator. Okay, so let's suppose I'm just looking at this. What do I do? Okay, well, these blue ones I don't really need right now because that just said, look at the numerator as its own problem. And I see this set of parentheses. So that says do everything in here before multiplying by 2. So I'm going to kind of ignore the 2 and those purples. And then I see addition, multiplication, parentheses with subtraction, and an exponent. So here we go, following what we know about repeated addition, repeated subtraction, and all the examples that came before, such as here, right? we want to do what's inside these parentheses first. Like this 10 plus 3 was 13, and that helped us. Let's go ahead and do this 8 minus 3 because that helped us. Instead of rewriting this as 8 minus 3 times 8 minus 3, which is how we would square it, and then rewriting that as a lot of additions and whatnot, let's go ahead and do the 8 minus 3 first. Okay, so step 1, these parentheses, 8 minus 3 is 5. Okay, so there's my step 1. Step 2, I'm thinking, oh, too much scratch paper on my desk. Step 2, I'm thinking, okay, now I want to write this down, but I don't have a lot of space. I'm going to write it right here. So now I'm thinking 8 minus 3 squared, because we do the exponents before the multiplication, like in example 4, where we computed 2 times 3 squared. So, and we said that this is 5 squared, and that's 5 times 5 makes 25. Yeah? Okay. And then, so we did this, then we did the exponent, like in example 4, and now we have a multiplication of 2 times 25. So 2 times 8 minus 3 squared is really 2 times 25, because we just said 8 minus 3 squared is 25. 2 times 25 makes 50. Okay, so I just wanted to focus in on that piece right there. Now I'm looking at purple in its entirety, which adds a 5. Okay, so 5 plus 2 times 8 minus 3 squared is equal to 5 plus, okay, well, 2 times 8 minus 3 squared was 50. So this is 55. So inside the purple brackets right there is 55. And now we multiply it by 2. We double it. Okay. So that means the numerator. Okay, so 2 times 5 plus 2 times 8 minus 3 squared is 2 times, we know this whole thing right here is 55. 2 groups of 55, how much is that? 110? 110. Okay, so that's our numerator. Got it. Now let's focus on this denominator and what's going on there. We have this lighter purple set of parentheses, or gray, whatever. It's purple to me, lavender. So the first thing I'm going to do is do -7 plus 4. A debt of 7, add 4 to this bank account, and we're down $3. We still have a debt of 3. Now I see that we have, okay, we've taken care of the purple parentheses. Yeah. And so now the next line is really reading 5 squared minus 2 by -7 plus 4 is really equal to 5 squared minus 2 times -3. Now that looks sneaky. Yuck, because we have a negative and it seems like subtraction, but it's actually multiplication. So just for my mind, I'm going to rewrite this as 5 times 5 minus 2 times -3. Okay, and that just helps me. So 5 times 5 are the exponent, because exponent comes before subtraction and multiplication. So that's 25. And then I would be subtracting this being multiplied, or so subtract or take away. 2 groups of -3. Well, two debts of -3 make -6. So 2 times -3 is -6. But now I am taking away a debt, so that's actually adding. Okay, I got 31 for the denominator. Okay, so what do we got happening here? What do we have happening? So our numerator came out to 110. Our denominator came out to 31. How many 31s are in 110? Great question. Glad you asked, Wondercat. 110 divided by 31. I'm guessing 3 groups. So 3, this is an ongoing decimal. So let's go ahead and round it. I'm going to wave my hands like the symbol says and estimate this to about 3. And should we go to 2 decimals? Since this is an 8 in the thousandths place, that would round to 500ths. Okay. So that actually took quite a bit of steps, but in the end, we really wanted to break this down into numerator and denominator. And the more I break it down, the simpler it is for my brain to tolerate, honestly. Yeah. This next one has yet again an implied set of parentheses. So it's not an absolute value, but it's a square root. And so that's an implied set of parentheses. Okay. So when I think about this one, I'm really thinking, okay, here's the implied parentheses. Do everything under the radical first. Okay. So first, I will look at this problem. Got it. Exponents before addition, because exponents are repeated multiplication. So this is really 3 times 3 plus 4 times 4. And if you want to write this out again as all addition, go ahead. Otherwise, accept that, multiplication is repeated addition. So this is 9. And this multiplication is repeated addition, 4 groups of 4 added together. So that's 16. And when we add these, we get 25. So we're really taking the square root of 25. Okay. Here. I don't really like it. So that's our original problem looked like this, right? And that's the square root of 25. Now we can do that operation. The square root of 25 is equal to 5 because 5 times 5 makes 25. So undo the square of this. And the base was 5. 5 squared got us 25. So 5 is the square root of that. Yeah. So just make sure you do everything under the square root before you take the square root because of those implied parentheses. Let's see. So what is our order of operations? If we're going to make sure that, multiplication is repeated addition, exponents represent repeated multiplication, division can be rewritten as multiplication, and subtraction can be rewritten as addition. And then distributing can be handled in 2 ways, doing the parentheses first or whatever. So that means that our order of operations, and I like to look at this as a stair step instead of PEMDAS, or please excuse my dear Aunt Sally, or something about, there's many different sayings for this in order to get our memory to get it glued. But I like to think of it as a step. Do parentheses first, then exponents as we see them. So zero in on the parentheses, compute that first. Like when we zeroed in on this 8 minus 3. And like here where we did this 10 plus 3, that made our job quicker. So 0 on the parentheses first, then take care of the exponents, like in this problem, right? And then after exponents, now I'm thinking, what about multiplication, addition, and subtraction? Like all of those operations. Well, multiplication was repeated addition, like in number 1. So we multiplied first. But we also saw in example number 2 that if we had division and multiplication, we could actually do what from left to right, they had equal footing. So division and multiplication have equal footing. So if you see it, it's from left to right. So divide and multiply, or multiply and divide from left to right. And then after multiplication and division are done, then the last step is to do additions and subtractions. I will make a comment about this up here too, though. Subtract and add, they have equal footing. So I'm going to do a similar thing with multiplication and division, left to right, such as when we saw number 3, where because we can rewrite subtraction as adding a det or same as a takeaway, by the way, and then doing all addition. So because of that, they have equal footing. We go from left to right for it to work out. I will make a little caveat here that one of the things that confuses students and people doing math in general, or computations in general, is that something like number 6 and number 7 add this last thing whereby you had to do these overall parentheses before you did this step of division. So what you really want to do, in my opinion, the best way forward is to put in, oopsie, just colored on my own sheet, that's okay, is put in these implied parentheses that are not showing up, because that will make you do this first and then the division. All right, as a quick summary, for section 1.3, order of operations, yeah, you verified and used properties of real numbers, adding and subtracting, multiplying, dividing, all of that, yeah. You interpreted and used operation symbology, and you established and correctly used the order of operations to simplify numerical expressions and equations. And let me tell you, sometimes they're not pretty, right? Just got to break it down into one thing at a time, one step at a time. And then that way you can do the correct order of operations.